All right, so here's this problem with the window on the side, okay, or the gate on the side there. And so you can see it down there at the bottom. Here it is. All right, there you go. All right, so our job is to find the force that's acting on that gate. All right, now the way that we're going to do that is we are going to use our little trick where from calculus, where we're going to say that a force is equal to a bunch of little forces. Okay, so we're going to need little tiny forces here, a little df. Okay, now since a force is a pressure times an area, that means my infinitesimal force, my df, is pda. Okay, just like so. And so my p is rho gz, my depth. My dA, all right, is going to be what I'm going to call y dx. Okay, now that's my dA element. The dimension that goes into your screen this way, all right, that's what I'm going to call y. All right, so in our case here, where it says there's a width of 2 meters, we're going to take that to be y is equal to 2. All right, so x is, whoops, I don't want to have an x on there. That needs to be a z. Okay, let's get rid of that because we're not integrating in x. We're just going to integrate in z. There we go, just like that. Okay, so I want to take my expression here for my df and put it back up into my integral. Okay, so what we're going to get is rho g y z dz. Okay, and our limits are going to be from the top to the bottom. All right, so I'll call it zt and zb. All right, because we only have force along this area right here. Okay, so that we got to limit our integration to that range. Okay. All right, so rho gy comes out front. Those are just constants. There's my rho gy. Okay. And then what I'm left with when I have that is, well, I'll go ahead and write it out so it's not confusing. Okay, then I've got a z dz here. Okay. Now if I do my antiderivative, I got rho gy 1/2 z squared from z at the bottom, z at the top to z at the bottom, which means my force turns into 1/2 rho gy zb squared minus zt squared. Okay, just like this. Now I'm doing this a little bit differently than your book does it. The way I'm showing you to do it is it's more generic. Okay, and because of that, it's actually a little more powerful. I want you to keep seeing how we build these things out, setting up our integrals, okay, that sort of thing. So that's why we're doing it this way. Okay, but anyway, there it is. Okay, and so all I need to do now is to put in my numbers. All right, so I'm going to have 1/2 onto 1,000. Okay, now notice up here it says a million. Okay, that's 1,000 kilograms. So I need to do everything in CGS. 9.81. Not CGS. Sorry, we're not using CGS units. That's centimeters, grams, seconds. We're using MKS. Icky. Meters per second squared. I think I'm losing it, you guys. Y is 2 meters. Okay, and then we're going to have Z at the bottom, which is 5. Okay, and that's meters squared minus 3 meters squared, just like this. Okay, run the numbers on that through my calculator, and what I get is 156,960. All right, and that is newtons. Okay, it's newtons because we got kilogram, meters per second squared. Okay, and actually that's kilogram per meter cubed. And so I'm going to lose meter, meter squared, meter squared. I'm going to lose all those guys to end up with kilogram meters per second squared, which is a Newton. Okay, there we go. Now, I want to explore a couple other things while we're here that are important to know how to do. All right, now this one doesn't ask for anything other than the force, but what if it asked about the moment? Okay, what's the moment on the gate about the point A? How would we do that? Well, it turns out then what we would do is we would set up a different sort of integral. We'd say that our total moment was a bunch of little tiny moments. Okay, and so we're going to have some distance r down to our df. So that's going to turn into an r df. Let's call that a capital F there. Okay, now my r is a function of z. Okay, but I'm starting at 3, and so my r is actually going to be z minus 3. And my df is this rho g y z dz that we've had before. Okay, and so if we kind of run with that for just a little bit here, we're going to have rho g y, and my integral then is going to turn into z squared minus 3z dz, and then we're still going from 3 down to 5. Okay, just like that. All right, so if I do that integral and I plug in all my numbers, what I end up getting is this number here, 170,040. Okay, and that's going to be in Newton meters in the end. Okay, now, so that's the total moment acting on the gate from the pressure. Okay, and we might want to say also, so where's the location of that force? Okay, something we've talked about before. Okay, so if we're going to say, oh, all that force here is concentrated at what depth here? Let's call it Z0. All right, so in order to define that, what we're going to do is we're actually going to go that we've got, this is our radius here, so let's call that R0, okay? And we know that what we're going to have is R0 times the force we found is going to have to be equal to M, okay? And so that means our R0 is M over F. Okay, so we've done that kind of thing before, so we got 170,040 divided by 156,960, and what we end up getting there is 1.083 meters. Okay, so our actual Z0 is going to be 3 plus that, so we're looking at 4.083 meters would be the point of concentration of our force. Okay, so if we had to put all of our force at one place, then we'd have that. Okay, now one more thing before we leave this particular example. All right, and again, this is a thing that's not in the example, but you are going to run into a situation where they're going to ask you for, instead of just a hydrostatic force, they may ask for something like this. They may say a force per unit length or width or something like that. Okay. Now, when they're doing that, what they're saying they want you to do is take this guy right here and move it over there. So you're going to end up with F over Y, okay, and that's going to be your rho G Z dz. Okay, so one of your homework problems is going to ask for that kind of thing. It's not going to give you the width of this. It's not going to give you that Y dimension. Okay, we'll just pull it out of the equation. and you just run with what you have left, and you end up with a force per unit length type situation there, okay? Alrighty. Not too bad. Let's do 2 more.